So continuing on with the discussion of how to make the neopixel driver circuit, in the last video, we went through the master clock, how to get the counters to sync everything, and the D flip-flop and the rationale behind the D flip-flop. And I used transistor-based gates to make this portion of the circuit work. So in this video, I'm going to talk about the last part of the circuit, which is how to generate high and low monostable pulses from the master clock. And this one was the most challenging portion of the exercise, and I'll explain why. So in order to design the circuit properly, you need the master clock, which once again is operating at 800 kilohertz, and it's providing a relatively long duty cycle, at least 80%. And I explained that in the last video because when you AND this with the low and high pulses, you want it to encompass at least the entire duration of the high pulse. This master clock then goes to you want it to, well, it's going to the counters. It's going to the D flip-flop to sync everything. And now you need it to go and trigger at the same time a high pulse and a low pulse. As I talked about before, the high pulse has to be at least 800 nanoseconds long, and the total period should be 1.25 microseconds. And the low pulse needs to be about 400 to 450 nanoseconds long, and the total period should be 1.25 microseconds. Well, the period's not the problem because we have a 1.25 microsecond period if the clock goes at 800 kilohertz. Now, I'm going to talk about the way this should be done, and then I'll tell you why it didn't work for me and why and what I did to compensate for it. So the correct way to do it is to have this master clock going into a monostable pulse generator. So the simplest thing to do would be to take a 555 timer. And here's once again, the 555 timer, the TLC 555 timer. And to wire it in monostable mode, you basically have to, pin 8 goes to VCC, pin 1 goes to ground, pin 2 is our trigger from the master clock, and pin 2 gets triggered on a low pulse. Pin 3 is our output. Pin 4 is our reset. That's just tied to VCC. Pin 5 is our voltage control pin, which we don't connect to anything, or you could connect it through a capacitor to ground. And so pin 7 and 6 are key here. And so you want a monostable pulse. And so the easiest way to generate a monostable pulse with a 555 timer is you need a resistor and a capacitor. to ground. And what happens is every time you put a low pulse here, this triggers the capacitor. This turns off pin 7, triggers the capacitor to charge through this resistor. And then the minute that pulse goes away, the minute it's charged, it goes above a certain threshold value, 2/3 of the VCC, the capacitor discharges through pin 7 to ground. And this total cycle is the formula for calculating the amount of time is 1.1 times R times C, the value of resistance, times the value of the capacitance. And so if you use a very small capacitor with a TLC timer, 555 timer, which can be done, you can use something like a 0.1 nanofarad capacitor and a resistor of, let's say, 4 kilo ohms. If you do this math, this will give you a value of about 400 nanosecond monostable pulse. And for a high pulse, you just increase the size of the resistor, you keep the same capacitor, you just use a different chip, and that value should be about 8 kilo ohms. That will give you about an 800 nanosecond pulse. So that is where the problem lies, because in order to generate these pulses, you need the 555 timer. You can't use a regular 555 timer. That's why I use the TLC 555 timer, which is a CMOS 555 timer. And originally, when I made this circuit, I used these two 555 timers, one to generate a high pulse, one to generate a low pulse, and these were all going into our AND gates here. High pulse and a low pulse going into our AND gates so that we can pick which one we want, and based on the data input, and into our flip-flop. So, and this goes out to the neopixels. The problem with this is that when I first started doing, first turned it on with the neopixels, what happened was the neopixels were going on when I had a high pulse. When I had a data 1, data going in was 1. When I had the low data going in, it would not turn off. It would not send a low pulse signal, and so the neopixels just stayed on and would not turn off. And it wasn't until I put an oscilloscope on there that I realized that the actual signals coming out of this, the actual output coming out of this, I could not get anything that was any pulse that was this low. I could get it to maybe 850, 900, which is still okay within the tolerance of the high pulse. So that's why the neopixels were turning on. But I could not, for the life of me, do anything to get this pulse low. And then when I looked at the data sheet of the the TLC 555 timer, in the fine print and the monostable mode, it was mentioned that the comparator inside this that does the triggering is a little slow, and it can have a delay of up to 1 microsecond to turn on and off, and therein lay the problem. If it takes a whole microsecond to turn a comparator on or off, and you're trying to generate signals that are less than a microsecond long in monostable mode, you're not going to be able to do this. You're not going to be able to accomplish this. And hooking it up to an oscilloscope at its at the smallest possible values, and I tried, 100 picofarad. I tried it with the smaller resistors with this, and I could not get the signal to be shorter than 1 microsecond at this clock rate. So there were two options. I could scrap the 555 timer for the monostable operation and get a different set of chips. I know that there are faster monostable 555 timers. There's an LMC 555, which is the fastest version in astable mode. This can go up to 3 megahertz in astable, and you can use even smaller components, external components with this to generate this. There's some other chips that I can't think of right now. I think 6538 that does quick one-shot pulses. So I very much thought about getting one of these or getting a different chip to do this. But then when I ordered flip-flops, I ordered 2 different flip-flops. I had a 74 HC-D flip-flop, and I got CD 4013 flip-flops that I used for a different project. And so when I ordered them, I used one flip-flop from each for different projects, but they come in like 10. So I had all these extra flip-flops laying around, and I was looking at the flip-flops with regard to one of the other projects that I did, and it turned out that each of these flip-flops worked very well when you triggered them and when you clocked in data. But each of these flip-flops, especially this one, have a certain propagation delay associated with them. Now, propagation delay is the amount of time that it takes to clock in a certain amount of data. This is especially longer when you use set and reset, which asynchronously turn on the flip-flop output or turn it off, turn on the Q and Q bar. And so each of these flip-flops, now this one is a little faster than this one, but the principle is basically the same. There is the internal circuitry of these ICs are such that when you hit set, it takes a little while to get to the actual output of setting the output high when you hit set, when you put a high pulse at set, and similarly with reset. And so with the CD4013B, this delay is up to about at 5 volts operating voltage. This delay is about 500 or about 300 something, 300 and change nanoseconds. So I'm thinking to myself, well, if I could get a pulse to go into set, and then I have the reset tied to high so that it's set. So after the propagation delay of this happens and the reset actually turns it down, that will be, if I measure the output at Q1, that will give me a high pulse, because it'll be at least 300 seconds to get this to go on. And once it's on, to get it to go off and then transmit back, when I measured that out, it was about 650. And then when you add the other little components to it, the other little components of the delay, in terms of rise time and data valid time and all that, it ended up being close to 800 nanoseconds. And when I did that, and I would send a set signal, and then a reset signal, and then the reset would automatically go, and I measured the output at Q2 or Q1, it would give me about 800 nanoseconds. And that was great because that was my high pulse. And then when I did the same thing on this D flip-flop, it worked just as well as this one, but it was a little faster. And when I did it to this one, I got a low pulse, or a pulse of about 400 nanoseconds. Because this one is so much slower at 5 volts, this is meant to be run at a higher voltage to decrease the propagation delay. But these are designed to only be at 5 volts. So the whole project is working at 5 volts. And so that is how I made my circuit. So I'll keep these handy. And so what I basically did for the high pulse is I had the clock input, the master clock, going to, if this is the CD4013, I basically had it going to the set of this. Then the reset, since it triggers on a positive voltage, I had it pulled to VCC, and then the output I took from Q, and when looking at it on the oscilloscope, it gave me a pulse of about 800 nanoseconds, which was perfect. And so all I had to do was tie the Q to the other side of the AND gate on the high pulse, and that was it. Similarly, for the low pulse, I did the exact same thing on, I had the clock going into the set. I had, since this flip-flop, the sets and resets are low pulse, are active low, I had the reset tied through a resistor to ground, and so the clock would activate it. This would assert the set, and then the reset would be tied low. And after all the propagation delays that went through all this, the output, if I measured it on the oscilloscope, would give me an output of 400 or so nanoseconds, which was the perfect low pulse. And this output I sent to the other side of the AND gate. This is our new low pulse. Low pulse measures, if this is 100 nanosecond divisions, 1, 2, 3 divisions, gives you about a 300 and change nanosecond high pulse, which is perfect for the zeros of these LEDs. And on top of that, to convert, this is done with a D flip-flop, a single D flip-flop, a 74HC74. And all I have to do is make it, and this is just the propagation delay in the circuit between the set and the reset. So all I have to do is switch this to there, and switch this, the clock signal, to the reset. And there it is. That one measures about 600 and change. So that is the high pulse. To test it out, all I have to do is touch the input of the LEDs to that. and it should light up the whole thing. So when I did that, I thought it would work instantly, but it worked a little bit, but was not quite what I wanted. It didn't respond appropriately sometimes. And when I looked at both of these outputs on an oscilloscope simultaneously, because of the various propagation delays, I would get a timing diagram that looked like this. And I'm going to show this, I'm going to add this to the video as well. But this was the high pulse, and this was the low pulse. And I would get something that looked like this. So I would get a high pulse. Let's see if I can make this go in the video better. So I would get a high pulse and I would get a low pulse, and they were pretty stable as monostable triggers, but they weren't in sync. And so when I wanted to deliver a low pulse, I would just get zeros being sent into the AND gate, and so I wouldn't get I wouldn't get a very good low pulse, because you want this to be in sync. You want these two pulses to be triggered at the same time and be running at the same in the same phase, basically. So these were out of phase, and so my thought initially to make this was to take this low pulse and then put it through an inverter, because I had now gotten some inverter gates, and so I put it through 74 HC, I think it's 04, which is hex inverter gate. That was great, because if you put it every time you invert this signal, there's a propagation delay in this hex inverter. But that propagation delay is about 15 nanoseconds. This is a quick chip. And so every time I inverted the signal, and you have to invert it twice, I would get it to go a little bit more forward, and then a little bit more. I put it through all six inverters on one chip, and at the end of that, I got it to basically look kind of like this, but it wasn't enough. I wanted the rise of this to be at about the same time as the rise of that. And so propagation delay, given all my recent knowledge about the propagation delay, I realized that what gives a TTL logic chip the propagation delay? Most of the time, it's the transistors. The transistors take a while. And so it turns out that when you take a regular NPN transistor, a 2N2222, which I seem to have a bunch of, that transistor has its own propagation delay. So every time you put a signal through this transistor, there's a certain amount of storage time and rise time and a bunch of other things. And if you look at the data sheet on the 2N2222 NPN transistor, you get a total of about 300 nanoseconds of delay time by using this transistor. And so I've made transistor-based inverters previously. If you could look here from the previous video, I drew it out. This is a transistor-based inverter. And it's a NOT gate. And when you need one NOT gate, and I made them before I had any of these chips, you basically take a signal that goes, that's the input. You put it through a 2K resistor, and the output of this transistor is from here and basically going through a 1K resistor to power. And this is basically on until you turn this on, until you apply a signal to this. And when you apply a signal to the base, the current flows preferentially down to ground in this common emitter, and this turns off because the path of least resistance is down. And when you cease putting a signal in, this turns on again because the voltage goes, the current goes in this direction. And it's a very good functioning inverter gate. And basically, to take a low pulse signal and invert it, you would need to invert it twice in order to maintain the same low pulse signal. So I basically put this through 2 inverters. And when you take the low pulse signal and you invert it using transistor inverters 2 times, one time it goes upside down, it inverts upside down, and the second time it inverts right side up. And at the end of that, I got a 600 nanosecond delay from these transistors, which was equivalent to this amount of delay that I needed to make. And so at the end of all this, if I had 2 side by side, here's the high pulse. I'm going to try to draw it accurately here. My low pulse looked like this. There was a little bit of a change in the shape of the waveform that happened with it, but for the most part, these occurred at exactly the same time. It didn't change the length of the signal. This signal was about 400, well, I think I measured it out to 405 nanoseconds. This signal came out to almost exactly 850 nanoseconds. And and the total period stayed the same at 1.25 microseconds. So now we had a synchronized high and low pulse. And when I plugged these into the AND gates, the neopixels lit up anytime I wanted them to light up and went off every time I wanted them to go off. To the point, it was as precise can be. So here is our high and low pulses on 2 separate channels. So if you can see here, the top pulse is the high pulse, which measures if each division here is 250 nanoseconds. Then the high pulse measures 1, 2, 3.5, which, measures out to be, let's put the cursors on, and measure it out to be about 805 nanoseconds. And the low pulse is about 1.5 divisions, about 400 nanoseconds. The clock is running at 787 kilohertz at the moment, and it's adjustable. The only problem is that the rise of the leading edge, the front edge of the clock on the low pulse is not synchronized with the clock on the high pulse. And I want them to be synchronized. So I was trying to delay the second circuit, the low pulse one, by a little bit. And I tried to use an inverter chip, this 74HC04, which it's a hex inverter. And The problem is the propagation delay of this inverter is only 15 nanoseconds. So when I inverted it 6 times through all the stages of it, I only got a tiny bit of delay. So instead, I used 2 transistor-based inverters, and you can see them right there. One transistor there, one transistor there, and it's a 2N2222 NPN transistor. And when I use the transistors to delay the circuits, let's connect this up and see what we can do here. Now I have it connected properly, finally. Sorry it took so long. Now I have it going through those 2 transistor-based inverters. And now, if you could look at the way the signal comes out, the leading edge and the trailing edge, or the leading edge, is now in the right position. The leading edge starts when the other leading edge happens. So, you know, any deviations from this are probably breadboard related, but now you can see it measures about the same. Let me adjust the clock a little bit. There we go. And now we have a high pulse and a low pulse that start around the same time. And the high pulse is exactly what we want it to be, and the low pulse is exactly what we want it to be. And so the final circuit, basically, for this was, and I'll draw it out here, master clock, 800 kilohertz, and what this, and I have it going to CD4013B, which is the CMOS D flip-flop, dual D flip-flop, and a 74HC74, which is the 7400 series D flip-flop. This went to the set, this went to the set. In this case, the reset was tied to ground. In this case, the reset was tied through a resistor. This went through a resistor. It's a fairly, you know, you could use any resistor, but it's got to be like at least, you know, 5K or so. This one went to VCC. Let's call it a 5K resistor. And then the Q of each of these went into the AND gate. That I had over here. And so this was coming from the Q of this flip-flop. This was coming from the Q bar of this flip-flop. And all together we're going through a pair of diodes, basically a discrete component based, this is a 1K resistor to ground, and this was going out to the neopixels. And that is our final completed circuit. This would provide, but before this went into the AND gate, I should fix this. Before it went to the AND gate, let's put it through here. I put it through VCC, ground, resistor there, the output of which went here through another to the base of another transistor, VCC, ground, and the output of which went into this AND gate. And this provided a double inversion, and at the same time a 600 nanosecond propagation delay that allowed for my two signals to be synchronized. That way we have an on-demand availability of a high pulse or a low pulse, and depending upon what we tell the flip-flop to do, based on the data input, there's going to be constant high pulses and low pulses coming in here, but they won't be turned on unless we want them to be turned on based on the output of the Q or Q bar here. And so they would be ANDed with one of these, and whichever one of these was on, the other one was off, and so on and so forth. And then that would go through this diode-based OR gate into our neopixels. And this worked like a charm. So that is the complete neopixel driver circuit. The next video we'll talk about putting some data into it and how to put some data into it. The simplest way to check it is to just put a oscillating signal that you could adjust at various rates, and it'll give you interesting patterns coming out of here. But that is the completed circuit. This is our final schematic, and it would have been nicer and more elegant for these high and low pulses to be generated by a monostable pulse trigger, and didn't have to make it in the Fugazi way, which is with the propagation delay on the flip-flops. This would have been the nicer way to do it. And for those people who want to make something like this, I don't use the TLC 555 or the regular NE 555 timer, but if you could find a monostable pulse generator that can be triggered by the master clock and be able to deliver a short enough signal of 400 and 800 nanoseconds, and you know to calculate these are fairly quick. All you need is because the nanofarads end up corresponding to nanoseconds, you just have to if you can take this number and multiply it out, and it ends up being somewhere like 400 when these two numbers, that will give you enough of a value, enough of a timing requirement to make 400 nanoseconds, and the other one for 800 nanoseconds is even easier. All you need to do is basically, if you have this size of a capacitor, 0.1 nanofarad is just 100 picofarad, right? And so if you take that and you just multiply it by whatever first number you want, and then in the thousands, you get 400. If you, in 8 kilo ohms, you get 800. And this is fairly precise, provided that you have a fast enough monostable pulse generator. So there are faster monostable pulse generators out there. This is one of them. There's a couple of other ones. They're not that much more expensive. They're just a little bit harder to find. But they are available, and you only need 2 of them for this. Of course, they always come in packages of like 10 or 20, but you only need 2 of them. And so that is our final circuit. please let me know in the comments if you have any questions, and I'll be happy to answer them. Thanks for watching, as always.